colleagues, I would like to introduce the research on topic ultrasonic pretreatment for enhanced air filtration in pharmaceutical cleanrooms. Clean air in pharmaceutical environment isn't just a recommendation, it's a requirement. Especially in sterile and high-risk drug areas, we need to ensure every cubic meter of air is tightly controlled. That's why air quality in production zone is strictly regulated by the standards like European Union GMP Annex 1, USP 797, and national guidelines. So, how is this achieved? The process starts by bringing in outside air and filtrating it step by step. First come pre-filters, which catch large dust particles. Then medium efficiency filters like MERV 8 to 13 catch finer particles. This protects the most sensitive filter that comes later. Next, air goes into the air handling unit, where it's heated or cooled and humidity is adjusted. Fans inside the unit maintain constant airflow. The most critical stage in the filtration is using HEPA or ULPA filters, which remove over 99.999% of even the tiniest particles. This whole system is typically managed by the Make-up Air Handling Unit, or MAH. It combines all major components, filters, coils, humidizers, fans, into one system that conditions the air and keeps everything stable and compliant. It's essential for maintaining pressure balance and preventing cross-contamination. HEPA and ULPA filters trapping particles down to 0.3 or even 0.12 microns, but that efficiency comes with a cost. These filters are expensive, and because they have such a fine pores, they tend to clog over time, especially in dusty or humid environments. Moisture can even cause fibers to swell or microbes to grow, which raises resistance and reduces airflow. That's why regular replacement is needed. And in pharmaceutical setting, that means downtime, validation, and high costs. To solve this, pretreatment strategies are used to protect the final filters. These include ultrasonic agglomeration, electrostatic separation, magnetic separation, and even chemical methods. The idea is simple. Reduce the number of fine particles before they reach the ULPA or HEPA filters. In our case, we are focusing on the specific strategy, ultrasonic pretreatment, developed under the RESPIRATION project, part of the Horizon 2020 program. The particular ultrasonic pretreatment uses acoustic resonators placed right before the filtration stage. This device generates ultrasonic waves that cause fine particles to stick together into the bigger clusters through a process called acoustic agglomeration. These clusters are much easier to trap with the standard filters, which means less clogging, lower pressure drop, and longer filter life. Modeling ultrasonic emitters critically important, as the components directly generate the acoustic field within the working medium. Their geometry, oscillation frequency, and extension method directly affect pressure and velocity distribution. Without accurate numerical modeling, it's impossible to predict where particles coagulation will occur or where the system may lose energy. This modeling is essential for the optimization and design and ensuring stable performance under real operating conditions. Advantage of using the fine element method include prediction of resonance surface motion and pressure distribution in air, determination of particle trajectories and coagulation behavior under ultrasonic pressure, optimization of geometry before fabrication. This reduces experimental loads and speeds up technology development. As part of the RESPIRATION project, advanced computer modeling was created to investigate how high-frequency ultrasonic interact with the fine particles suspended in the airflow in duct with the resonators. The main objective of the simulation was to understand and quantify how resonant acoustic field influence particle agglomeration and how these effects can be enhanced by introducing a resonator structure into the flow channel. A new simulation method was developed in the project to accurately model the mechanical behavior of ultrasonic emitter and its coupling with the surrounding air. The main task of the method is to determine the directional displacement of the emitter as a mechanical system and export it to the selected computational fluid dynamic solver. The first step is determining the natural frequency of the emitter and identifying the modes where maximum surface displacement occurs in the required direction. To determine these frequencies, the model ANSYS analytical system could be used. The system is assumed to be free, no external forces, and undamped. This made to simplify the analysis, focusing on natural frequencies and mode shapes. The solution assumed harmonic motion. After determining the natural frequencies and selecting the optimal frequency, the next step is to establish the directed surface deformation of emitter, considering the influence of the surrounding fluid. This task can be solved using the harmonic acoustic ANSYS, which allows not only to simulate of sound wave propagation in the acoustic domain, but also account the fluid effect on the emitter's surface under the fixed boundary conditions. Harmonic acoustic determines surface deformation along all three axes. This deformation can be used as boundary condition for CSD. The next step is to export the obtained directional deformation into a CSV file, which can be used as the user function for modeling boundary condition in CFD. Since the imported file will contain only maximum values, a sinusoidal changes at the frequency determined in the model ANSYS must be applied to account for the oscillational effects. The new simulational method improved the precision of energy distribution modeling and enabled better prediction of resonance zone within the duct. It also allows to achieve a more realistic representation of the operating condition and provide critical insights for refining the physical design of the acoustic pretreatment units. As a result of the applied method, the pressure distribution and velocity vectors of the surrounding medium under the influence of the emitter surface were obtained. The analysis of the results shows good agreement with the experimental and theoretical studies by the other researchers. As for the conclusion, it can be noted that a new modeling method for ultrasonic emitter surface oscillation is proposed, which accounting for displacement in all directions. The method integrates modal and harmonic acoustic analysis to define realistic surface deformation, and CFD to define pressure and velocity distribution. The model shows strong agreement with the experimental data, and the method reduces reliance on physical experiment and accelerates the development of ultrasonic system for particle coagulation, chemical process, and environment technologies. Thank you for your attention.